Hello, my name is Madison Room, and I am part of Project 21075 titled Continuous Raw Sugar Production. My team members are,
I'm Jane Fairchild.
And I'm Corey Baracaldo.
and we are all chemical engineers. So the objective of this project is to design a plant that produces sugar crystals with a sustainable process, both environmentally and economically viable. As you probably know, sugar is an essential part of a person's diet, making it one of the most important commodities in the world. Sugar crystals can be produced from sugar cane or sugar beets. However, in our project, we are using raw sugar cane. Moving on to material and methods, the plant is a continuous steady state process. From calculations performed at these conditions, the plant's production of sugar crystals was found based off the initial input of raw sugar cane arriving at the plant each day. Another big aspect of the process design is to produce ethanol to sell as fuel to ensure that the plant is economically viable. To create an environmentally sustainable process, we are recycling the steam in the system, which saves the plant energy. Additionally, a cost analysis of the project revealed a series of project costs and earnings that will be discussed in more detail later. I'll now hand it off to Corey to elaborate on the project's goal.
Thank you, Maddie. So here's the overall goal of this project is to produce sugar crystals from sugarcane. And this is done through a continuous process to minimize shutdowns. In this process, we're also going to have steam produced from the solid waste, which is also known as bagasse, and that steam that's produced from it will be used to save energy through the evaporators, which we will discuss later on. In this process, molasses is also produced, which is an undesired product, and that will be used up to make ethanol and fertilizer, which we can sell for a greater rate. Here we have the process flow diagram, where the red lines indicate where the main process, while the blue lines indicate where steam is produced. And here we will go over the main process to turn sugarcane into sugar crystals. So we start from sugarcane imported from the fields. Once the sugarcane is imported, we crush them so that it helps to extract more sugar. Once they're crushed, the sugar juice is separated from the solid waste. The solid waste will be burnt to make steam, while the sugar juice will then be evaporated to further concentrate the sugar, so there will be less water in it. Once that is done, it will go through a crystallizer, and that is where the juice will then become crystals. In addition to the sugar crystals, molasses is produced as a side product, and they will be separated using a centrifuge. The sugar crystals will be ready to be sold, while the molasses will then be sent to a reactor to produce ethanol and fertilizer. And now, Jane will talk about the production outcomes.
Thanks, Corey. All right, so with this plant design, we plan to process 1,300 tons of raw sugarcane per day. Through a series of mass balance calculations, applying laws of the mass conservation, of course, this starting amount will allow us to produce around 1,500 tons of our main raw sugar crystal product, 1,100 tons of our ethanol product, which will be sold for transportation use, and 30 tons of vinasse fertilizer product. With the same mass balance, again, following laws of conservation, the bagasse from the mill will be sent from the burner for steam production, and the amount of steam produced from there will be around 700 tons from the bagasse. The evaporator will also be producing around 8,200 tons per day of steam, which is the water evaporated off of our sugar solution. Both the steam from the burner and the steam from the evaporator will be used to reduce the amount of energy provided to the evaporators. Our process will require a total of 5.7 billion kilojoules per day of energy, or 6,600 kilowatts. This value was found using energy balance calculations, which follow the laws of energy conservation. However, it was also determined that the steam from the bagasse burner alone provides around 1,200 kilowatts of energy, allowing us to reduce the amount of energy put into the evaporators from 2,300 kilowatts to 1,200 kilowatts. Burning the bagasse to produce steam reduces our energy requirements, but it also decreases our waste by reusing it elsewhere in our process. I will pass this on to Effie now to discuss our environmental aspects.
Thanks, Jane. The two largest pollutants we have in the sugar industry are carbon dioxide and wastewater. Our facility is estimated to produce 550,000 metric tons of CO2 per year. Just to put that into some context, the aviation industry has a 2019 total 918 million metric tons of CO2. We plan to address our CO2 problem in the future by using methods such as carbon mineralization and direct-to-air capture. But however, this is outside of our scope for the current project. For our wastewater around the world and in the US, this is generally dumped into water supplies such as lakes and rivers. However, in the US, the NPDES only allows a certain amount of pretreated wastewater to be dumped into the national water streams just because it contains BOD, COD, nitrogen, ammonia, nitrogen, phosphorus, and suspended solids. And all of these are toxic to marine life in large amounts. To combat this, sugar refineries and ours as well incorporate sub-plants for wastewater treatment. And we would also incorporate this as well, but just right now, this is outside of our current project scope. Worker safety is paramount to us, though the level of particulate matter is lower than the allowable limits. Repeated exposure has been linked to certain health-related risks, such as impaired lung function. We also have some fire hazards, as the sugar crystals are a combustible dust, and in mass accumulation have led to certain incidents in the past, such as imperial sugar. And also, since the equipment is very hot, the workers have potential to be burned, as well as the slippage due to the moisture in the atmosphere. The particulate matter is weighed down and is collected. So to protect our workers and our community, we would follow certain OSHA and EPA regulations. These EPA regulations that we would follow, such as the Clean Air Act, would limit how much CO2 we can emit into our atmosphere. And these OSHA regulations that we would follow, such as the safety and health standards and the respiratory protection, would help protect our workers against some of the illness and process hazards. I'll now turn this over to Maddie, who will talk about our economics.
Thanks, Efe. So here we have the summary of the economics of the project. First, there is the total bare module cost, which is essentially the total cost of all the equipment, which was found to be about $33 million. Next, we have the total capital investment, which is defined as a sum of cash acquired by a company to pursue its objectives. This value is found to be about $220 million. Finally, there is the annual net earn of the project, which is about $62 million. This takes into consideration the sales from the sugar crystals and ethanol and the total cost of the plant, the sales being about $506 million. The biggest contribution to the sales of the plant is the ethanol sales, which keeps the plant profitable. There are also a handful of economic risks that could affect our project, such as fuel, raw material, electricity, and water prices. These prices have varied over the past 5 years and will continue to change, which will affect our process. And that concludes our presentation. Thank you for watching.